Hi, everybody. We are back with our topic of discrete time systems. So let's get started. What we are going to do today is try to finish this module that we are dealing with. We started dealing with in the last lecture, namely how discrete time systems can be analyzed and how controllers can be designed directly for discrete time systems. So we're going to look at simple cases of discrete time systems for which controllers can be designed directly. And of course, the more interesting ones are systems for which we have multiple inputs, multiple outputs, and of course, those are naturally handled by a computer, which naturally works in discrete time, okay, at every sampling point. Last time we talked about basics. Let's very briefly discuss these. So we have here a process. There may be some disturbances to the process and some manipulations that we provide to this process, and it produces a signal Y over time. So that signal is sampled. So there is a device here that creates a digital signal from this continuous signal. So the digital signal is just like the one above it, except we only look at specific values over time, something like this. So this is y at times tk or just yk. And this may be t0, t1, t2. And that's why we say discrete time, because we looked at discrete points. Those are distinct points. Each pair is separated by a certain time. We can call it delta t or h. There is no uniform notation for that. But this is the sampling period. And we explained that the sampling period should be roughly 1/5, 1/10 of the dominant time constant of our system. And what is the dominant time constant? If I throw a step to my system, the output is going to respond like that, assuming it's stable. And there is an approximation of this response by a dead time from here to here. And a first order response, 63% of the total response is within one time constant. Okay, so that time constant tau rather, goes here. If we sample the output of such a process every 1/10 of its time, because they're not going to be good enough. We're not going to miss much from what the process produces. So the digital signal, then there may be some noise here in the measurements, which is natural, and there are disturbances. Like I said, this is sent to a discrete controller, a discrete time controller, which needs to know set points, it needs to know perhaps constraints, and produces an input to the process. And that's what closes the feedback loop. Okay. The thing is that now the connection between the computer which is the controller in the process, needs an analog to digital converter because the computer produces sequences like this. But what actually goes to the process is a signal like that. This is time, this is U of t, this is tk, U at tk, or U sub k. And as we explained several times, we already know how to express the connection between this continuous signal and that continuous signal. We have transfer functions that tell us very well how the input U creates an output Y. We can write differential equations, we can write transfer functions, we can develop models. We'll see actually how we can get such models experimentally. So that's something we can understand. We'll see more about that. The computer, on the other hand, sees things that are of this nature, namely you have this measurement. And from this measurement, the computer generates that manipulation in discrete time. Okay? From points in time, it creates other points in time. The question then is, how does the computer do it? How does the computer do this calculation to take Y and from that generate U? Well, that's what we're going to cover today. And I'll have to provide a warning that this is going to be a little dry in the sense that there's going to be a lot of sequences and indices I, J, K, and all that, which humans don't like very much because we're not very good at processing multiple integers at the same time. What the computer actually feels very comfortable with. Give an array to a computer, it does things very easily. Right? We'll do this on Excel, by the way. Solve just a couple of examples. Feel comfortable. But we humans like pictures and continuous things and all that. So try to go back and forth in as exciting a way as possible so we can maintain some intuition and some sanity actually in all this. Okay. So section 9 in the notes on page 15 in the discrete time systems notes says from continuous to discrete time system models in the time domain. What is this thing and why do we need it and what is it useful for? First of all, we already explained that yellow is continuous time. Blue shade is discrete time. Now, we understand how to build a model in continuous time, yellow U to yellow Y, but we need to understand also how the computer works, how C, the computer controller, the digital controller, takes Y in discrete time and produces U in discrete time. For that, we'll have to use a discrete time model and a discrete time controller. And sometimes the controller uses the model explicitly, and we learn how this is called. This is called the IMC idea. The IMC idea, we learn it in the context of continuous time systems. The same structure carries over to discrete time systems. A lot of the machinery that we learned in continuous time systems carries over to discrete time systems. In fact, on page 23 rather, I have collected in table 1 tools that are available for discrete and continuous time systems, discrete on the right, continuous on the left. This is a symbol-heavy table. There are lots and lots and lots of symbols. But the nice thing is that you don't need to do all of these calculations suggested there by hand so that you can analytically derive solutions and all that. Most of that stuff will be done in the computer. What you need is the qualitative behavior of these tools. So we'll cover those. Back then to section 9 of the nodes on page 15, where we are learning how to go from discrete to continuous time systems. Why do we need that? Again, because we can build model-based controllers, for example, using the IMC idea. Let's remind ourselves what this is. So if we have a G process which is stable, and this is a manipulated input, all the disturbances, we lump them into one signal, which may be the output of and some of many other signals. We just lump them all into one disturbance, D. This is what we measure. There may be some noise, and we said we take that around. We compare this to the set point, and we put the controller, and we say this is the feedback loop. But we also explain that we can take this signal, pass it through a model, and subtract model, G tilde, subtract this from the measurement, and then feed that signal back. This signal here is y minus G tilde u. And then we add that signal and combine everything, and eventually instead of this, we have Q here. So this Q and G tilde that we have here, this whole thing, oops. This is our IMC controller. I forgot to put the minus sign here. Okay, so this is our IMC controller. And why is this useful? Because we explained if we have the original connection between set point and Y and disturbance and Y, and let's say noise and Y, and maybe we can have a disturbance on the input U. Let's leave that aside. We know that all the denominators are this, and the numerators are this. We've done this several times. So this is 1, and this is minus GC. And we said if we call this Q, then we can nicely represent everything in a way that presents a very simple structure which has only G and Q, and everything is in series, and stability of the closed loop. We get from this simple idea here, we get that Q stable is necessary and sufficient for closed loop stability. So if Q is stable, then the closed loop is stable, and vice versa. If the closed loop is stable, then Q must be stable. There is no other way around. This also implies that since we want to make this about 1, and this about 0, and this about 0, we have a design objective, which is make Q approximately equal to 1 over G, and 1 over G must be stable. If it's not stable, we have to modify it somehow. So Q must be 1 over G. And if we have that, if 1 over G is stable, we said that Q is equal to 1 over G times F. We saw that in continuous time systems, right? This is our beautiful IMC design, which gives us in half a line various capabilities and limitations of feedback. This design, for example, tells us that the best response that we can get here is just the filter f if 1 over g is stable. So 1 minus, this is if q is equal to 1 over gf. So this is f y set point plus 1 minus fd minus f. And then this is going to be on indeed about 1 at low frequencies omega. This is going to be about 0 at low omega. And this is going to be about 0 at low omega, but about 1, sorry, the other way around. Omega, about 1 at, sorry, the other way around. Okay, this is going to be at low frequencies. We're going to have all these set points will go through, and at low frequencies, yeah, so low omega, and at high omega here. So let me make sure I get this right. So again, 1 low frequencies, this. So I'm doing this from memory, so I have to check, make sure I get this right. And this gives us capabilities and limitations of feedback immediately, as we have already mentioned. For example, it says that low set point frequencies can be followed well by the output, but because most of noise is at high frequencies, that can be cut off because this is almost. Say it again. No, this is f, not the frequency content of noise. It's what f is, right? Remember, f is, let's say, first order, it has this form, logarithm amplitude ratio of f versus logarithm omega, right? It's about 1 here, and it's about 0 at high frequencies. Okay, so high frequencies don't go through. Low frequencies do go through, but noise is mostly high frequencies. Low frequencies are not there so much. If you have low frequencies noise and you make set point changes, well, you have to do something else. All of these things that we mentioned can be actually translated to direct designs in discrete time. We can design discrete time controllers. And for these discrete time controllers, we, of course, need this model here. And in addition to a model, in continuous time, we had Laplace transforms, which allowed us to do multiplication. We didn't have to deal with differential equations anywhere. It was just algebra, so we can understand capabilities and limitations and design and all that for our system. We could understand the objective, for example, as I said already. We could understand the capabilities, this and that. We can understand the limitations. We could understand that the inverse response cannot be eliminated, dead time cannot be eliminated, all those things. To do these things in discrete time, we need to be able to build models in discrete time. And in discrete time, we have difference equations as opposed to differential equations. So for continuous time, we have to solve differential equations. There's plenty of good software these days, and you can use Euler's method in Excel to solve differential equations. But difference equations, just say the next value is equal to the previous value plus something. So that you can do on Excel. You don't even need much sophistication. We gave an example last time. For example, it was example 4 where we let's do it very quickly. So we have a tank, in and out. We have the differential equation AdH over dt. H is the liquid level. It's equal to inlet flow rate minus K, the square root of the height. And we look at two outputs, y1 of t. In example 4 is K square root H of t, y2 of t is equal to H of t. So one easy way for linearization, so for discretization, so discrete. And again, notice this is here an ODE, right? It's a differential equation, so we can discretize it and make it a difference equation. One easy way is to substitute this derivative, as we explained last time, by a finite difference. So you have hk plus 1 minus hk over delta t, a is equal to fi at time k minus k square root h of k, and y1 at time k is k capital H sub k, and y2 at k capital, k lowercase is h sub k. All right, we've seen those things many times. These are called the output equations, and they are algebraic. This is called the state equation. We just put one. We'll see we usually have many more, but I'm just keeping it simple. So this is my system in discretized form. It's approximate, but nevertheless, it's good enough to deal with this now in discrete time. I can simulate this on Excel. I can just create a simple sequence. We'll do some of that as we go along. In fact, we can actually do this right now. So simulation with discrete time systems is very, very simple. It can be done with sophisticated software. Simulink allows you that, especially if you do things in the transfer function domain. But Excel is good enough so you can simulate those things easily. So let's see what we're going to simulate while Excel is starting. We're going to have columns that say what is H, given the U, which is the inlet flow rate. And we'll see this at, let me make it a little better. So at K, where K is 0, 1, 2, 3, at time Tk, where Tk is 0 times delta T, 1 times delta T, 2 times delta T, keep going. And we have H sub K and Fi K. And of course I can create now, so this is going to give me the state equations, which is this here, and y1 at k, one column, and y2 at k, another column. It's all that I'm going to build on Excel. And this equation here, I'm going to write it in a more convenient form because I want the next value of h to be equal to hk plus delta t over a, k minus a squared hk. Incidentally, this is numerically called Euler's method. It's a method for integrating differential equations such as this very easily numerically, known to Euler at least 3 centuries ago. But Euler didn't have computers, but now we have computers. So actually this can be used easily for numerics very, very nicely. It's trivial to program. In fact, let's do it together. So let's say that I jumps from 2 cubic meters per minute to 4 cubic meters per minute. Let's say that H initially was at 2 meters. So let's say that K, the time constant, is 1 with corresponding units. You can figure those out. So let's put this into our equation. So first of all, before we do anything, just I is equal, we said, from 2 to 4. So initially it's 2, sorry, this will be whatever it is, 2, and we'll change it to 4. We have that H0, we don't need that. We need K equal to 1, A equal to, what is the cross-sectional area? Let's say it's, oh, let's say, how much? 0.8 square meters. Good enough. This is just simple small vessel. Okay. We don't have any other parameters. Oh, delta T, our integration time. Our sampling period is 0.1, sorry, say 0.1 minutes. Minutes. I don't think we'll need anything else. Let's do our calculations, our beautiful simulation. So K takes values from 0 to 1. Etc. etc. Let's name these. We start. Okay, so we have TK, T sub K is equal to this number times our dt. So we can have these times. Our H sub K starts from, pick a value, 2 is whatever. And we'll see what comes after that. If I at K, we said is going to be equal to 4, jumps from 2 to 4. And then we have Y1K is equal to what again? Y1K is K capital square root HK. So it's equal K square root HK. And Y2 is equal to just HK. Okay, so these are our starting points. Now, how HK evolves over time depends on this formula that says the next value is equal to the previous value plus delta T over A times the previous Fi minus K square root previous H. Let's put it all there. So it's equal to the previous H plus delta T over A multiplied by the previous Fi minus K times square root of the previous HK. Okay, so copy this down. This. 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 So let's plot this to see what we have created. Okay, so this is showing what, we tried different way. This. Okay, this is a little cleaner. So, where is H?
H is behind 2K because you just have them 2K equal to H.
Say it again.
In your Excel, you just have 2K as equal
Right.
to H, so it's hiding it. So that there's the same value.
Okay, great. Thank you. So this is our simple simulation. It's not long enough. Well, if we want more, we can go down and get more. And this shows actually, oh, hold on, I don't want this. I want this way. So let's see what we created, if it's this. Okay, so this is what this is showing here, right? And if I simulate it a little longer, it's going to give me something that reaches a steady state, so that I can get a pretty good idea. You get the first, this output here, which is the outlet flow rate. The outlet flow rate gradually matches the inlet flow rate, as this is indicated here. Orange is the inlet flow rate. This is the outlet flow rate here. The gray, this is the level. So everything is fine. In fact, this indicates that if I take a larger sampling period, this is still a pretty decent approximation. Let me do this now. Actually, let me make it 2. This is still a decent approximation, nothing blows up, and I could take an even larger period. This is still a nice, decent approximation. Okay. As a matter of fact, this can tell me roughly how frequently I should be sampling, because I can think of this as a first order response, right? This is about a first order system, although it is nonlinear. So I have to be very careful, but nonetheless, I look at something that behaves almost like a first order system. Well, 63% of the change from, let's say, 2 to 16 is 14. 63% of that is how much? About 8 to 9, right? So it's about here that I would go to the right and check down here. The time constant is about 3 to 4, roughly, for my system, correct? So if my time constant is about 3 to 4, a good sampling frequency, a sampling period rather, will be about 1/10 of that. We just explained, right? So 0.4 is about 1/10, so that's pretty good, okay? If we go higher, we'll start pushing it, so we can go higher and double it. Let's see what happens. Still okay. That's still a good approximation. Doesn't look like I'm missing. And now I'm combining two things. One is an approximation of a continuous time system by a discrete time system. And second is a numerical solution of differential equations. It's the same idea here for this example. If I overdo it, the approximation is not going to be good anymore. The method actually is going to result in some sort of instabilities. This is, sorry, 1.6. So this is still good, but if I go to much higher, let's make it 10 to blow it up. This starts having oscillations, and 20 will blow it up. 30, it blows it up. It shows it goes here and then it stops. This clearly says that my system simulation is not very good. You see that num here, all the blow-ups here, right? And this is not 30 minutes would not be a reasonable sampling period. A reasonable sampling period would be 0.4 minutes. That's pretty good. My system works. So the theory that we learned works well in this simulation. The simulation actually has a dual purpose, as I already explained, to give us a sense for A, how we solve numerically such systems, very, very easy with Euler's method. And B, if I pretend that this is a discrete time system, we sample every 0.4 minutes, this is a good approximation of what we would see, what the computer would see. And it's a good idea. This is not in the notes because this is material from the typical undergraduate numerical methods course, but it's a very, very simple idea, how we approximate derivatives by finite divided differences. We are going to see actually that we can get around this approximation that we did here, where we took the derivative and approximated it by finite divided difference. So to be perfectly fine, this should be approximately equal, not equal. It turns out that if my system is linear, there is actually a very good way, an easy way actually, to create a discrete time system which matches the continuous time system exactly. If I have continuous lines and I sample these lines, my model predicts the points exactly, not approximately. And this is useful for controller design. It's a better model and all that. To do all this, we need a little bit of machinery, which is similar to Laplace. And before you protest that, oh, this is already too much, so why do we need another method? Well, the method is called Z transforms, and it's actually simpler than Laplace. Laplace transforms take continuous functions. So they take a continuous function, f of t, and create a Laplace transform f of s. Z transforms do the same thing, but in discrete time. So they take a sequence of points, f sub k, and create a Z transform that I'm just going to call Z. In the same way that with Laplace transforms, this S is actually a placeholder. Z is a placeholder here as well. It's just a convenient way of carrying forward all the information I need so I can find stability, speed of response, design controllers, and all that. And even though there is a definition of how I go from a sequence to the Z transform, I'm not going to do the definition because we can use these Z transforms very, very well without the definition. We just need, in this case, 3 simple facts rather than 4. Here we had 4 facts. Here we need only 3. So we can use these Z transforms very easily. What was the first fact with Laplace transforms? You probably remember this. That was 2. Yeah, so the Laplace of e to the minus AT. The first one was ridiculously simple. It is what? Linearity, quite right. So Laplace and inverse Laplace are linear. Well, in the same way, Z and inverse Z are linear. Which basically says, first of all, this arrow can go in this direction, as can this one, of course. So you go to the right by Z, and to the left by Z inverse, in the same way that you go to the right by Laplace and inverse Laplace. There is a formula also for inverse Laplace, a general formula through a complex integral, and I'll refrain from using this because we're not going to need it. It's very, very mechanistic and very easy. So for Laplace, we learned that the one basic Laplace that we need to remember is this. With this, we can go practically all the way because A can be real or complex. If it's real, the inverse of this is an exponential. If A is complex, it will always appear with its complex conjugate. And then we have, in the inverse, we have exponential times. When we invert this and A is complex, the inverse will have exponential times sinusoids, exactly, periodic term. Well, it's the same with Z transforms. It's actually a simple idea, which is of the same nature, namely the Z transform of P to the K, because K is time now and it is discrete, right? So this is P to the 0, P to the first, to the second, third, fourth, fifth, power, etc., etc., is equal to, it's again a fraction, and it's of this form, 1 minus P Z inverse. And of course, this is equivalent to the inverse of this is e to the minus AT. This is section 10 in the notes, right? The operational calculus for Z transforms. So same thing, of course. Self-explanatory. Inverse of 1 minus P Z inverse. This is our basic second property. In the same way that when Laplace had 1 over S plus A, and if A was real, we had an exponential. If A was complex, then we had exponential times sinusoid. We have the exact same situation when we have Z transforms. You see here that this is P to the K. Well, if P is real, nothing to worry about. Z inverse of this is just that, just an exponential where the exponent is discrete. If P is complex, so if P is complex, then the inverse is still the same, but we know that there is also another pole, which is the complex conjugate of P. And I already used the term pole because P is a value that makes the denominator, if Z is equal to P, what is the value of the denominator? 0, exactly. So because that value of Z equal to P makes the denominator 0, P is called a pole. So poles are the values of P that make the denominator 0. And in the same way, the values that make the numerator of a Z transform equal to 0 are called zeros, just like Laplace transforms. So if P is complex, as we're showing here, then there must be a P bar. And then from these two, actually, here, we can get that the inverse of 1 over 1 minus P Z inverse, there's going to be, so if we do partial fraction expansion, etc., there will be a coefficient here, R, and there will be another coefficient R bar here, minus P bar Z inverse. And you take the inverses using this formula here, and you go. And after you go a certain way, you get eventually that the inverse is, well, if you said exponential times trigonometric, you guessed right. It's the same thing. So this is equal to something. I'll put the something. It's rho to the k. That's an exponential term. Again, k, did I write this explicitly? So k is, of course, 0, 1, 2, 3, etc. Right? That's always. Times a trigonometric, so cosine theta plus k phi. And there is something in front of it. So this is what we call an exponential term. This exponential in discrete time. And this is trigonometric, cosinusoidal, where it has, this is again discrete time. So this is discrete time, this k. This phi is frequency, and sigma and rho are found from the following. This coefficient R here is equal to rho e to the j phi. If we write this coefficient in polar form, which you have explained several times, rho is the magnitude of R, phi is the face of R, and j is the imaginary unit, j squared is -1. We get this. Finally, let's do the last one, fact 3, and then we'll do some examples, numbers, just to feel comfortable. So 3. What was example 3 in Laplace? Let's put it actually down here. Oh, dead time, okay, let's do dead time. So f of t minus theta is equal. Yeah, very good. E to the minus theta is in, let me use, instead of theta, there is theta on the right. Let's make sure I don't confuse things. Tau d, so it's tau d is dead time, td rather is dead time. Well, it's the same thing in Z transforms. Nice, and there was minus the initial condition. Sorry, no. This was for the derivative. Let's look at that now. The fourth fact, that's where I want to put that. Where is the fourth fact? For Laplace. It's the fact that helps us go from derivatives, Laplace of derivatives, to functions. So Laplace of the derivative is related how to the Laplace of the function? Yeah, minus f of 0. It's a simple mechanistic rule. Where you see a derivative, you put s. If you see second derivative, s squared. Third derivative, s cubed, and all that. So, as a matter of fact, it's an interesting story. People actually discovered these things even heuristically without connection to Laplace transforms. They figure that, gee, if I use something that says this is a derivative, I call this an operator. The second derivative is operator square, operator cubed, and all that. And they did a whole calculus with operators alone. And then it turned out that actually this is nicely laid out in the context of Laplace transforms and so forth. Well, same story for Z transforms, but it's even better because the two transforms here are actually just one. And that is Z of that shifted sequence. So the sequence GK is equal to f at k plus 1. right? So it's just one element further. How is that it related to the Z transform of the sequence F sub K? Well, it turns out it's a similar thing. You have here K plus 1, you have here K, you just need Z to the first minus Z times the initial condition. If the initial condition is 0, you have 0. That term. Now that can be extended if you have 2, 3, 4, etc. You have here, you can apply this again and again and again and again. And you'll have initial conditions here, and you'll have, sorry, here you'll have Z squared, that's the interesting thing, Z cubed, and so forth. Let's do some number crunching to feel a bit more comfortable. That's it. That's all the algebra. All this. Okay, it's very, very simple algebra compared to Laplace transforms, perhaps easier. Let's do some examples. Example 5. Z transform inversion. This is the counterpart of Laplace transform inversion for this nice simple f of z, which is in the form 0.5 z inverse 1 minus z inverse 1 minus 0.5 z inverse. How am I going to invert this? Well, before I do anything, why am I writing this as polynomials or first order polynomials in z inverse rather than in z? Well, this is because I want z inverse rather than z, because that's the one that I need to use. Okay, so it's even though polynomials can be written as functions of powers of z or z inverse, I prefer z inverse here because it's so much easier to use my basic fact. Now, this I'm going to invert using the same technique I used in Laplace. If I had Laplace and I had something 0.5s, 1 minus s, 1 minus 0.5s, how did I invert this? What steps did I take? Partial fractions, partial fractions expansion, and then invert each fraction, right? Which is easy. Well, I'll do the same. I'm not going to do it again because it's fairly straightforward. So 1 minus z inverse minus 1 minus 0.5 z inverse. And then you can confirm that if you put those together, you get the result you want. All right. So if I have this, I can invert it now. Take the inverse, which means I can take the inverse of this and the inverse of that. Let's go to the second one. What is the second inverse? Well, let me look at my cheat sheet. I said I'm going to need basically these 3 basic facts. Which fact can I use so I can find the inverse of this? The second, and the inverse of this will be, yeah, 0.5 to the k, or k equals 0, 1, 2, 3, etc., right? All right, and there is a minus in front, so I'll put that there so I can have the whole thing, minus 0.5k. All right, how about this? 1, because it's 1 to the k, so it's just 1. And now that I have this, I can plot it actually. I can plot this thing. So if I have k, and this is f sub k, the sequence that I just created, let's plot it. So for k equals 0, what is f sub k? 0, and then k equal to 1. So this is T0, T1, or sorry. So K0, 1, 2, etc., etc. or this corresponds to T0, T1, T2, etc. I'm sorry. Go ahead, please, for k equal to 1. Yeah, 5. And it's very easy. Now, eventually, where is the sequence going? As I have more and more and more here, where is it going to go? Point 0.5 to the k, as k goes from 1, 2, 3, 4, etc., etc., it becomes 0.5 is 1/2, right? So squared is 1/4, cubed is 1/8, 1/16, 1/32, 1/64, blah, blah, blah. As k goes to infinity, where does that 0.5 to the k go? 0, exactly. And 1 minus 0 goes to, yeah, 1 minus 2.5 to the k is 1. So this is the final value here, to which this goes asymptotically. It's the favorite joke between an engineer and a mathematician, right? There is a pot of gold here, and there are two runners here ready to cover that distance. One is an engineer, one is a mathematician, and there is a genie that says, every time I blow the whistle, you cover half the distance. So this is half, this is this point, this is half of the remaining distance, this is this point, half of the remaining distance, this point, and going and going and going and going, and asymptotically you go arbitrarily close to this, although you will never go exactly at this point, right? And of course, the engineer keeps going, the mathematician stays there. Why does he stay there? Well, you know the rest of the story. I don't need to belabor the point, right? There is always going to be 1/2 of something left for the mathematician. That's why the mathematician doesn't do anything. The engineer says, well, I'm going to be within engineering approximation. So this is what this describes. And in fact, this example 5, it's a nice, simple, innocent example, but we can get more from this example because we can interpret this f of z as the response of a simple system to a step change at its input. Let's see that. So we have that f of z, no, let me open that. F of z is this expression. So I can make this f of z to be the transfer function corresponding to part of it, which is 1 minus 0.501. And there is an input and there is an output. So the input is a unit step change. So it has these values. At all points in time, the input u has these values, 0, 1, 2, 3, 4. By the way, for values of k less than 0, for negative values, my functions are 0. It's the same thing as with Laplace transforms. Functions before 0 time are all 0. Okay, so this is my unit step change. So my input changes by 1. And I want to find what will be the response of that system. Now, before I do this, oh, sorry, got this. Before I do this and find what my y is, which I already identified up here, let me find what is the equation that describes the system. So I have that in the z domain. Let me be somewhat careful with my notation, and then we'll be just use just convenient notation. So this is the transfer function that connects y in the z domain to u in the z domain. Can I find the difference equation that connects these two, y and u? When we dealt with Laplace transforms, we did a simple trick, which was the reverse of going from ODEs to Laplace. And we went from Laplace to ODEs by, what was the trick? multiply by the denominator, precisely. So if I multiply by the denominator, apologies, I'm talking, okay, sorry. It's this thing. Okay, obviously. I apologize, this wasn't planned or meant to trick you. It was just an honest mistake. The output is the transfer function times the input. Apologies. So this times the input gives me times the output gives me the input. And now I can go back to the time domain. So I have 1 times y of z. If I go back to the time domain, it's going to be y sub k. And now I have 0.5z to a something, y of z. The inverse of that would be, well, it's linear. The 0.5 will come out. And z to a something times y of z, when inverted, would give me yk plus something, so -1, right? There's a -1 here. I'll have a -1 here. From what fact did I deduce this? In my z domain cheat sheet. It's not 2. 2 is about this. It's 3, yes. If I have k plus 1, it's z to the plus 1. If I have k minus 1, it's z to the minus 1. The initial conditions are discarded because, as we explained, Laplace transforms, they have a transient effect. So this is the inverse of the left-hand side, and the right-hand side is 0.5 uk minus 1. And if I want to write this in a somewhat more convenient form, this is yk plus 1 is equal to 0.5 yk plus 0.5 uk. This is my beautiful difference equation. And those equations are used all the time, not only for controller design and for simulation, but also for identification. In practice, the common problem is to identify these two, which is going to be our next chapter in the notes. The identification PDF that describes how we can take experimental data and find these numbers. And what are these numbers? Once we know these numbers, we are okay. And of course, this immediately sets the question, does the next value of the output depend only on the previous values of these, or could it depend on values in more distant past, or could this y not be there, and so forth? We'll see all these ideas again and again. So this was example 5. Again, example 5 showed that we can do Z transforms easily mechanistically. And in fact, there is significance to what this mechanistic exercise gives us, because if we have this Z transform, whose inverse is this, we can think of this inverse as the response of a first order system that has this transfer function g of z, and there is an input to this system. Actually, I'll put, there is an input to the system. There is a 1 here. That input is u of z, 1 over 1 minus z inverse. So that input here generates this output that we just created there from 0.5 to 1 all the way. Okay. And that's a very, very simple case that illustrates the value of these things. You can get more elaborate cases. To give you an idea, I have in the notes example 6, which I'm going to leave as a homework note to hand in, because it takes a lot of algebra, but there is nothing new there in terms of what we did here and how to extrapolate that to example 6. The only thing that we need to take into account is now in example 6, P is not real, so the inverse is not P to the K, it's this thing here. So example 6, let me just give the beginning and the end of this example. Example 6 says if I have the Z transform 0.91 Z inverse 1 plus 0.84 Z inverse plus Z to the minus 2, then you split it into partial fractions, and first of all, and I just see a typo. The partial fractions are 3, 1 minus Z inverse plus 1 minus 0.2 Z inverse, and there is a plus something that is a typo somehow. I cut and pasted that, I'll fix it. Make a note. So this is a typo there. So for that transfer function, then you take the inverse of this, you do it nicely, and you have eventually so this is easy, and it's this here, this thing. So the inverse of this is simple, the inverse of this is simple. This is the one which is the one we are really interested in. Well, actually, as I'm looking again, it's correct. It has the whole thing as I'm talking about right now. One more time, let's continue our discussion. So there is algebra in the same way, and it is 3, which is actually the inverse of that is 3, plus the inverse of this is 0.2 to the k, which is simple, and the inverse of this is sine 2k. So the exponential is rho to the 1. So there is just a constant there, which is also 1, and that is the final result of this. I'm going to leave that as a homework problem, not to hand in. The reason for that is because there is more interesting material that is described in example 7, which is Z transfer function of first order plus time delay. So first order plus time delay says, let's look at this. So we have y prime of t, tau t is equal, rather, plus y of t is equal to k u of t. How would I get the Z transfer function in this? Minus theta, minus the delay. How would I do this? Well, I would discretize this, yk plus 1 minus k over delta t. And I would take Z transform, so the only thing is that this would be a delay, so I would have Z to the minus theta over delta t. That would be a term that would multiply this u of Z after I would take the Z transforms. Paul says zeros, I already mentioned that. Then I have something that is about transfer matrix in equation 27. Let's postpone that until we do multivariable systems, so it's not there. Let's look at the Z transform as another example, discretizing a PID controller. We have mentioned that. It's worth taking just a second. So we have said several times that the PID controller says the output from the controller is a function of the error. And it's what function of an error? It's proportional to the error plus an integral of the error with approximate weight plus derivative of the error with appropriate weight. And the error is, of course, set point minus weight. We can approximate this in discrete time, and we explain how you take the derivatives of both sides, and this becomes d over dt is kc dt plus 1 over tau I e of t plus tau d, second derivative with respect to time. And then this is approximated by uk plus 1 minus uk over delta t. This is approximated in the same way. T, and the rest is straightforward. E sub k, and the second derivative is approximated by ek plus 1 minus 2 ek plus k minus 1. And now we have that the next value of this depends, the current value of this rather depends on the current value of the error, and it has the previous and one more than the previous. Take z transforms, and you have these z transform functions. Finally, before we conclude with our controller design, which we'll explore next time, and then the reverse, how you get the models that go into controller design. Section 11 says from continuous to discrete time system models that done in the transform domain. Why bother? Because we said if we have derivatives, and we say in place of this at tk put this difference, well, this is approximate. How can I create a model of this form, for example? I want to create a discrete time model that doesn't use an approximation. I want things that have yk plus 1, blah, 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 blah. I want this to be exact. I don't want it to be like this. Well, it turns out that there is a simple process. Well, there's a simple formula through a lengthy process, but it's very, very explicit, and it will be done by software. You will never do this by hand. But it's worth mentioning because it's as follows. If you have a continuous time transfer function, P of S, there is a discrete time transfer function, G of Z, which is not P of Z or anything like that. It's a lengthy derivation that goes as follows. You first multiply this by e to the minus st over s. Take the inverse Laplace. T is the sampling period. Let's say delta t. Sampling period. Take the inverse Laplace of this, then sample it, and then take the z transform of that. And that will give you g of z. And the nice thing is now, if you have input and output, the distinct values that this g of z produces are exactly the values of the continuous times system at the corresponding sampling point, which is very useful for control purposes because it doesn't matter how long the sampling period is. You will always get exact matching between continuous and discrete. You can take that formula and eventually get, well, there is example 9 that shows how to apply this formula. And this is just, it's optional, obviously, because this shows you how lengthy the algebra is. You can generalize this into theorem 3 on page 20 that says, give me P of S. This is my starting point. I'll give you immediately G of Z, the transfer function in discrete time. And I'll do this as follows. If I have P of S written in the form first order plus time delay, and this may be actually sum of first order transfer functions. So that means I can have any transfer function with time delay, however many of those you want. Well, this corresponds to, so this is P of S. This corresponds to the following G of Z. It's equal to, this part is B1 A1, 1 minus e to the minus A1 delta t, divided by Z minus e minus A1 delta t. And this is going to be plus the same start with 2. So B2, A2, 1 minus e to the minus A2 delta t, Z minus e to the minus A2 delta t. And you may wonder, why am I now using Z and not Z inverse? Because it's simpler, okay? If you multiply numerator denominator by Z inverse, this becomes numerator times Z inverse, 1 minus blah, blah, Z inverse. That, and final Z minus the integer part theta over delta t. That's it. And why is this so useful? And why bother? Because when people do experiments, as I have in the PDF that has this heavy oil fractionator, let me try to make it a bit more clear. So it's I don't see. I'll find that PDF and it's actually, let's go to our canvas. Here, chapter 3 from Pratt and Garcia, Fundamental Process Control. This has a heavy oil fractionator, which is shown here. This is in the schematic. You see all the control valves, the level control loops and all that. And you see here the transfer functions in continuous time. Those are all first order plus time delay. Those are from experimental tests. And you see here, they convert these in discrete time. So it's lots of algebra. You'll never, ever do this by hand. You'll have to do it once, maybe twice, so you know what software does. I have homework, actually, that will help you do these things, along with solutions using MATLAB, so you can just visualize those things. And the whole idea is to know what this means. And we know what this means. This means there's a delay of 7, for example, here, and this first order because the denominator is first order, and all of these things, right? And from that point on, then they can use this to apply on all these criteria with constraints and objectives and all that, which we'll cover. So as I already mentioned at the beginning, unfortunately, this is a somewhat dry lecture because we need all that machinery so we know how to go to here, from here, and in fact how to get all this from data. Okay, so we already know now roughly all of that. In the next lecture, we'll see a few applications of the things we already learned with numbers and specific controllers and just visualize a few things. And then we'll move on to the more challenging part, namely if I have some data from experiments or operating data, how well can I estimate my model? And why do I need my model? Again, because I need this matrix to do advanced control. I cannot do advanced control without that matrix. Okay, so I'll stop here then. And next week, we're going to discuss, to close this chapter and move on to the identification PDF, which is the reverse, how from data we get a model. Quick note, identification relies on statistics and doing linear regression. I trust that all of you at a certain point, you may not have done anything sophisticated, but you had to fit a straight line almost certainly, right, at one point. So it's as simple as that. It turns out that you can do actually a lot more even with Excel. You don't need very sophisticated software to do fitting of data, even for control problems. We'll see. We'll do a little bit of that. We'll pretend we have some data, fit some models, and understand when the data is good, when the data is bad, when the model is good, and when the model is bad, and so forth. So I'll stop here and we'll continue on Monday with that part. Before I forget, homework 2 now, it's homework 1, we have covered it well already. Homework 2, you need to start doing that because you already know enough to get it done.